This is the last section of chapter 10 that we're going to do. So we're going to look at areas and lengths when we have polar equations or using polar coordinates. Okay. So if you think about the way that we find the area of a region when we have Cartesian coordinates, so we have some function y equals f of x, say you were to graph it. The way that we find the area under the curve is we just, look at the left bound of x and the right bound of x, and then we just integrate from a to b of y, which is f of x dx. Okay, and so basically, why does that work? Let's review that. So this integral is really like an infinite sum starting at a and going to b, and we're adding up an infinite number of these rectangles. And the height of the rectangle will be whatever the height of the curve is, so that's where we get our f of x. And then the width of the rectangle is dx. Okay, so this is I'll call it the length, and this is the width. And so that would be the area of that rectangle at this particular value of a, and then we would move, our x, and then we would move through every possible value of x starting at a, going to b, adding up all of those rectangles, and then after we add them all up, we have the complete area. Okay, now the strange and tricky thing and the crazy thing about calculus is we've got an infinite number of these rectangles, and we add them up and get this finite area that's under the curve. Crazy. Okay, so when we're looking at area under a curve in a Cartesian coordinate system, that makes sense to add up all of the rectangles. But when we move to the polar coordinates, and we think about a polar, we don't measure value like x doesn't move in a sort of linear way from one point to another. Okay, so when we have our polar axis and our pole, and the theta is our parameter, kind of the thing that's changing. Okay, we're moving. Oh, here's a theta, here's a theta, here's a theta. We're going through these angles. The region that we were trying to find the area of and figure out, okay, well, we're going to just chop it up into many pieces and add up all those small pieces. Well, if you look at what the small pieces are, they don't look like rectangles like they do for the Cartesian coordinate system. In the polar coordinate system, the pieces, the sort of slices that we're adding together, look like sectors of a circle instead. Okay, so when we do the formulation, it's going to be slightly different because here it's just y times dx, because that's the area of a rectangle, the length times width of a rectangle. But that's not how you find the area of a sector of a circle. Okay, so we're going to our polar coordinate system. Like I said, that slice of the region is not a rectangle, it's a sector of a circle. So we're going to need to use the formula for the area of a sector of a circle, which is 1/2 the radius squared times the central angle. And this has to be measured in radians. Okay. And so when we do that, the area of our representative slice, like this gray one that we've looked at here, is, well, this is 1/2, the radius squared times delta theta, or the change in the angle. Okay, so here's our delta. Okay, here's our angle down here. So that would be each individual. So if we had each individual one is going to have a different r value. So this one, that's our f of theta star. This is going to be different. This is based on whatever our curve is, based on our f of theta. Okay, so if we add up this one plus this one plus this one plus this one plus this one, so if we add up all n of those, we'll take the sum from I equals 1 to n of 1/2 of this f of theta star squared d theta. And then the way that we take and turn this infinite Riemann sum is the same as the integral. Okay, so the approach is exactly the same as what we did when we developed the formula for the area of a region in rectangular coordinates or Cartesian coordinates. But here we just have to make sure that we're using sectors and the area as the areas that we're adding up rather than rectangles. Okay, all of this means that the area formula for a polar region, when we're looking at the polar region where the angle is between A and B, it's just going to be the integral from A to B of 1/2 f of theta squared d theta. And often, instead of writing f of theta, we'll use an r instead. So here we might write this as r squared instead. So the area is the integral from A to B of 1/2 r squared d theta. Okay. And so again, it's just helpful to think of the area as being swept out by a rotating ray. It starts at the first angle and then it rotates along to the second angle. Okay, so that is how, that's the area that we're finding. Okay, so let's look at an example. So we want to find the area enclosed by one loop of the four-leaved rows r equals cosine of 2 theta. So it's probably a good idea to get a little picture of this in our mind first, especially if we want to figure out, they don't tell us what theta values we have to use in this problem, so we're going to have to figure that out. So you might want to pull out your kind of helpful representative sheet of polar curves. Okay, I know that it's r equals cosine of 2 theta. Okay, so here's the ones down here. We know it's a rows. They already told us that. So these are the cosine ones. Okay, so cosine 2 theta. So if we have an even number as the coefficient of theta, we know we're going to get twice as many petals. The length of the petals will be whatever the coefficient of cosine is out there. Okay, so for r, the coefficient on the outside, there's an applied 1 there, so the length of the rows of the petals is 1, and then we're going to have 4 petals, and then we're going to have this symmetry around the polar axis here. Okay, so with the cosine, all of the petals always are symmetric around the polar axis. All right, so that helps us draw a picture of this. Okay, so we're going to get something that looks like this. Okay. And now we just want the area enclosed by one loop. Okay, so let's go ahead. Maybe we'll just do this one right here. So this is just one loop, or basically one petal. Okay. And so if we think about that, we're going to have, okay, here's our A, and then this right here, this is going to be our B. Okay, so let's just call this negative pi over 4. Okay, that's just easier to do than calling it, whatever 7 over 4. And this one will be positive pi over 4. Okay, so if we go from negative pi over 4 to positive pi over 4, that angle will sweep out, okay, this entire petal. Okay. All right, so that gives us our bounds, and then we know that the area is going to be the integral from A to B of 1/2 of r squared d theta. Okay, and that's just straight from the formula on the previous page. Okay, so we figured out what A and B have to be. That's B from negative pi over 4 to pi over 4. Let's go ahead and pull 1/2 out front. Usually that's helpful. And then r, so r is cosine of 2 theta. When we square that, we'll get cosine squared of 2 theta. Okay. And so, a good substitution. Notice if we have, really we think about cosine squared of, I'll just call it u. And we usually replace that with 1/2 of 1 plus the cosine of 2. So we can do that same kind of thing, but we don't have a u. Okay, we have a 2u. So just have to be a little bit careful when we do that substitution. Okay, and so this is negative pi over 4 to pi over 4. So we're going to replace this with 1/2 1 plus the cosine, and then we need to make sure that we double the angle that we're taking here. So this one's going to be 4 theta. Okay. All right, let's go ahead and pull that one outside too. So we're going to get 1/4 the integral from negative pi over 4 to pi over 4 of 1 plus cosine 4 theta d theta. Okay, and so when we take that integral, well, the integral of 1 will be theta. The integral of cosine of 4 theta will be 1/4 sine of 4 theta. And that will be evaluated from negative pi over 4 to pi over 4. Okay, so when we put pi over 4 in there, we're going to get pi over 4 plus 1/4 the sine of 4 times pi over 4. Let me make these. And then we'll do minus, and then negative pi over 4 plus 1/4 the sine of 4 times negative pi over 4. Okay, and so the sine of pi is 0, so this is just 0, so this will be pi over 4 plus 0. The sine of negative pi is also 0, so this is 0, so we get negative pi over 4 or plus pi over 4. So this is going to be 1/4 of pi over 2 or pi over 8. Okay, and so at least for if we have, you know, a 1 out here, one of these leaves will be pi over 8 for the area. All right. Next, let's look at the area that lies inside the circle r equals 3 sine theta, and outside the cardioid r equals 1 plus sine theta. Okay, so once again, it's probably a good idea for us to get a picture of this.